And our last talk is about new security notion for conditional decryption in fully homomorphic encryption, and it will be given by Bhuvnesh.
Yeah. Hello. So my name is Bhuvnesh Chaturvedi, and I will be presenting my paper titled IND-CPA, a new security notion for conditional decryption and fully homomorphic encryption. So this is a joint work with Anirban Chakraborty, Nimish Mishra, Antika Chatterjee, and Devdeep Mukhopadhyay. So in this paper, we have been dealing with a special setting of FHE, where the outsourced cloud server that is performing the actual homomorphic computation has the ability to conditionally decrypt the result of some of the functions, but not anything else. So to begin with, we'll start with a quick introduction of what actually fully homomorphic encryption is. So these are a class of public key encryption schemes that allows you the ability to perform arbitrary computations directly over the encrypted data without the need to decrypt it first. It also further ensures that the result of such computations remains encrypted as well, thereby ensuring that the server that is performing the overall computation remains oblivious to both the inputs as well as the outputs of the requested computation. Now this is actually required in certain application scenarios, say for example, outsourced medical diagnosis, where the hospitals sends the symptoms of a patient to an outsourced cloud server, which performs the diagnosis on the symptoms on the encrypted data, and the result or the diagnostic result of this computations remains encrypted as well. And this is something that is desirable because you do not want to reveal the symptoms or the diagnostic information of the patient. But then there are also other application scenarios where you would want the server to at least know the result of the homomorphic computation. Like say for example, we consider this spam filter, where the email service provider receives the email in an encrypted fashion. It performs the spam filter on that email in a homomorphic way. And as an output, it receives an encryption of a bit, which denotes whether the email is spam or not. Now at this point, the server does not know how to proceed further, given that, or rather whether to forward the email to the actual recipient or simply discard it. So one such solution to this problem is that the server can simply forward this encrypted bit to the client. The client decrypts it, and then based on the result, ask the server to either forward that email or to simply discard it. But then this will require the client to remain online during the entire process. And this is not obviously feasible in most of the scenarios. Like say, for example, if you're a professor and you're receiving hundreds or thousands of email on a daily basis for, say, for example, for a PhD opportunity or an internship opportunity, it is not desirable for you to sit in front of your computer and help your email service provider to distinguish between whether the email that you are about to receive is a spam or not. So a nice solution to this problem came in the form of functional encryption, where the client provides the server with a special key that corresponds to a function whose result it wants the server to decrypt on its own. So for example, in this case, the client simply provides a special key that corresponds to the spam filter to the server. Once the server applies the spam filter on a received encrypted email, it uses this special key to decrypt the result of that computation, and on its own, it gets to know whether the received email is a spam or not. On the other hand, the server cannot use this encryption scheme to perform decryption or anything else. So in a sort of way, the input or the actual input email result remains encrypted. But in this particular paper, we are trying to evaluate the security of this kind of setting in a malicious server scenario, where the server is not bounded to follow the protocol specification honestly, and it can deviate from it arbitrarily. So one such scenario is that the server can try to inject crafted noise into the result of the spam filter, and then use this ability of performing conditional decryption to observe the effect of this noise over the final result itself, whether the noise affects the final result or not. And the threat or the severance of this kind of attack is that, given that this protocol or this scenario does not involve client in any sort of way, so the entire attack can run on the server itself, and in a sort of way, the server remains undetectable, virtually undetectable, and the client oblivious to the fact that a server is trying to perform something maliciously. So to model this kind of scenarios, we came up with a security notion, which was evident from the title itself, which is called as IND-CPA, which is IND-CPA like IND-CPA with the ability of performing conditional decryption. Now, the read for this added security notion, even in the presence of this already present multiple like security notion itself, under which the security of the FHE schemes are already evaluated, is that like even though these security notions vary in the amount of power that the adversary have, they all share a common belief that it is only the client that can perform the decryption on its end, given that only it possesses the decryption key. On the other hand, we are dealing with a scenario where the server has an additional power to perform like decryption of certain restricted computations. So like any other security notion, in this case, we define our IND-CPA security in the form of a game between a challenger and an adversary. In this case, the adversary, apart from the normal encryption and evaluation oracle, is also given access to a conditional decryption oracle that takes a ciphertext C prime and then checks whether it does correspond to an encryption of f of m dash. If the ciphertext does correspond to an f of m dash, it simply outputs the message in the clear text. Or on the other hand, if the ciphertext does not found to be an encryption of m dash, f of m dash, it simply outputs a bot. So during the challenge phase, the adversary does not have access to this conditional decryption oracle anymore. And it simply sends like two equivalent messages to the challenger and receives at random an encryption of one of those messages. And at this point, it has to output which of the messages it received an encryption from. If it can do so successfully with a probability significantly better than half, then it wins the game. Now we move further and show that none of the existing practical FHE schemes are actually IND-CPA secure. And to do so, we based our attack motivation on the underlying mathematical hard problem called LWE, which basically takes an exact system of equation and add to it a small amount of noise value to turn it into an approximate system of equation. And suddenly, this kind of approximate system of equations becomes hard to solve even for a quantum computer. But the idea is that because the security of this kind of problem is based on the presence of error values, so recovering the error values is like equivalent to recovering the secret key itself. And this is something that we do here. So to provide an attack intuition, we just take a quick look of how the encryption and decryption process works in FHE. So in case of encryption, we start off with a secret vector S, which is usually a binary or ternary. We draw a vector uniformly from some distribution, that is A. We have a message M. We have the error, small error value, which is here it is E. And then we have some extra parameters like the modulus and the message scaling factor. So that encryption works by scaling up the message to encode it into the MSBs of the underlying modulus. We mask it off with like a dot product between the public vector A and the secret vector S. And then we add a small error value to ensure this security. And finally, we take a modulus of this. The decryption works as a two-step process where the ciphertext is unmasked first, which gives us a scaled message delta M plus E. And then we scale it down with a scaling factor delta, and we round it off. Here we can observe that the final decrypted message M, that is 1, is actually the same as the one that we encrypted in the first place. And the reason that this happens is because the underlying error, that is E, is actually is less than a certain bound, where here which is defined as delta by 2. On the other hand, if we keep everything the same and just change the error value and take it as say equal to 78, now we suddenly see that the result of the decryption is no more the same as the message that was encrypted in the first place. And the reason is that the error value is now beyond the error threshold bound of delta by 2. So how do we leverage this? So the idea is that given a ciphertext that is an encryption of f of x, which is actually obtained by running the function at the server's end, we simply first of all assumes the sign of the error value that is present in the ciphertext, given that it is unknown, and that is something that we are trying to recover itself. Say, for example, we take an assumption that the error value is positive. In that case, this error value is bound to be present in between the values of 0 and delta by 2. So in that case, we take this value of delta by 2, that is the extreme end of the error distribution, and we simply add it to the like the ciphertext C to obtain C dash. Now, one of the two cases might happen. Like if our assumption was indeed correct, in that case, the overall error goes beyond the error bound. Like say, for example, if our original error that was present in the ciphertext was, say, for example, 14. And if in that case we add this error bound of 64, what we get is the final error to be 78. And in the previous slide, we saw that once this error value crosses the final threshold, the ciphertext ceases to be an encryption of f of x, given that it decrypts to a value that is different from f of x. In this case, if you were to like forward this ciphertext or query this ciphertext onto the decryption oracle, conditional decryption oracle, in that case, the decryption oracle simply rejects this ciphertext and outputs a bot. On the other hand, if the overall error in the or the underlying error was indeed negative, in that case, adding this threshold bound does not lead to it to cross the error threshold. Like say, for example, if the value was say minus 52, if you were to add this threshold bound of 64, in that case, the overall error value reaches 12. And in the first example, we saw that this leads to a correct decryption, which implies that in this particular scenario, the ciphertext C dash remains a valid input to the conditional decryption oracle. And in this case, the conditional decryption oracle simply decrypts it and outputs the message f of m dash. So one can see that there is the output of the conditional decryption oracle varies between the cases when the error is below a certain threshold or whether it is beyond a certain threshold. And this is something that we leverage to ultimately recover the underlying error value. And the way we do that is in a three-step process. In the first step, we simply query the oracle using the original ciphertext to recover the underlying message. In the second step, we first of all recover the error bound, which is actually equivalent to recovering the sign of the underlying error message. And once the bound is determined, we use a binary search based approach to ultimately recover the error message. And the way we do so is by setting the initial and final value or the start of end or end of the range of this binary search to be 0 and delta by 2, which is the extreme ends of the the underlying message, possible underlying message. And then we simply proceed with the binary search where we compute the midpoint. Like the initial value should be from, like given that the bound is between 0 and delta by 2, the initial midpoint will be delta by 4. We simply take the difference between this midpoint and the extreme end, that is delta by 2, which gives us a value of delta by 4. We simply add this to the the input ciphertext C to obtain C dash, and we query the decryption conditional decryption oracle using this C dash. Now again, one of the two things might happen. If the error value is below the midpoint, that is it lies between the range of 0 and delta by 2, in that case, adding this delta by 4 value does not lead it to cross the threshold bound. In which case, the C prime is still remains a valid input to the conditional decryption oracle. In which case, it simply outputs, we receives an output of f of x. On the other hand, if the error value is between the midpoint and the other extreme end, that is delta by 2, in that case, the overall error crosses the threshold. In which case, C prime ceases to be a valid encryption of f of x, and thereby querying the conditional decryption oracle model now leads to a failure or a bot. So this difference between f of x and bot can be ultimately used in an iterative or recursive fashion to recover the underlying error value. And once we have this error value recovered and the message recovered, we can simply go from the approximate system of equation to the exact system of equation, and then we can trivially solve it to recover the underlying secret key. So we kind of perform these attacks in simulations where we observe that the attack vectors actually works for 3 of the practical FHE schemes, for TFHE, FEW, and BFE. For FEW, we observe that it requires a least number of decryption queries, primarily because the underlying error bound is quite small, and the length of the secret key is small. For TFHE or like for BFE, we currently observe that the number of decryption queries is less than that of TFHE, but that is primarily because we are tested this for the smallest parameters. And if we go for the largest parameters, the number of queries for BFE will outgrow the number of queries required for TFHE. So how do we convert this IND-CPA secure FHE schemes to IND-CPA C secure FHE schemes? And for that, we take a leaf out of this this kind of new protocols that are coming into the literature, which is called as verification using snarks or verifiable FHE. So in this scenario, the idea is that like apart from the computation, the server is also required to perform proof or to generate proof of honest computation, which it does by taking the output of the computation, the transcript of the entire computation, and then it uses a snark prover to generate a proof of honest computation. Then it sends back the proof along with the final computed result and the transcripts back to the client. The client first verifies whether the proof is indeed correct or not. That means the result actually corresponds to the honest computation that it requested. And once the verifier says that everything is okay, the client proceeds with the decryption and accepts the result. If the verification fails, the client simply discards the result. The problem with this kind of scenario is, again, you need the client to remain online during the execution of the protocol. So what we do is, we simply take this entire verification scenario plus the decryption scenario, and we use a garbler to generate a garbled circuit corresponding to this entire computation. And once the garbled circuit is generated, we offload it simply to the client or to the cloud server. Now the cloud can proceed in its own manner, that is performing the computation and generating the results and the associated proof itself. And now it uses this garbled circuit to first verify internally whether the computation is indeed correct or not. And once it's determined that the proof is indeed correct, in that case, it simply proceeds to the decryption or it outputs a bot. So just to establish the correctness and security of our scheme, we see that the correctness of our scheme is dependent on the correctness of the underlying snark value, which states that as long as the proof is generated honestly, it will always verify. On the other hand, if the second criteria is that is based on the correctness of FHE scheme, which says that as long as the ciphertext is generated or evaluated honestly, it should decrypt with a high probability to the actual value. So this kind of ensures that if we are dealing with an honest but curious server or a semi-honest setting, in this case, our construction will always lead to a correct decryption. That means it does not hamper the correctness guarantee of the ultimate protocol. Or introduction of this verifiability does not hamper the correctness of the underlying overall protocol. On the other hand, the security of our scheme is based on the soundness of the snark, which says that if the verifier generates the proof in a dishonest manner, in that case, the proof check will always fail, in which case, the garbled circuit will output a bot. And therefore, the server will not know anything about the or any other extra information about the correctness of the actual result or not. And also the garbling kind of ensures that the server cannot tamper with the output of the verification step to kind of trick the decryption step to accept that the proof was actually indeed correct, when it was not. So the final key takeaways of this slides are that, first of all, we need to be we need to be careful when we are giving certain kind of additional power to the server. Because as we saw here that even a simple additional power that you can just decrypt the result of a certain computation can actually be exploited by a malicious server to recover the entire secret key. Furthermore, we also saw that the existing notions does not does not capture this kind of scenario, and therefore we need to come up with an extra or the additional security notion to better capture this scenario. And then we saw that snarks is a powerful protocol or primitive that can be used to make this conditional decryption more robust, and therefore we can leverage them to make IND-CPA secure or IND-CPA secure FHE schemes and turn them into IND-CPA secure FHE schemes. So that is all from my side. And if you have any questions, I'm happy to answer them. Thank you.
Any question? Yes, please.
So this very last point that you have there, that you need to ensure that the server cannot tamper, it makes sense, but why would the server be able to tamper with the outcome of the verification? I mean, that's done client side, right?
No, the idea is that the verification is actually done on the server side itself. But
Then why would the server not be able to tamper with it?
That is because we are kind of garbling the entire thing inside a garble circuit. So because it does not know the exact point where the verification is being done, and the output of the verification is actually passing on to the conditional decryption part. But that is why we are using a garbling circuit to ensure that this particular portion remains hidden from the server.
Okay. I'll need to look into this more. Okay, thanks.
Okay, thanks.
Other questions? So maybe I can ask one. So
Sure.
in your attack, you basically use this your learning with error model. I'm wondering whether about other kind of scheme, have you considered attacks for this, say, group action?
Sorry?
So in your attack,
Yeah.
you basically tell this learning with error,
Yeah.
type model, right? So what about other types of, post-quantum schemes? So people are using group actions, etc. So have you considered, attacks for this kind of?
As of now, no, but maybe if it's possible, we can look it into the future.
Okay.
Yeah.
Okay, thanks. So, any further questions? So if not, so let's end proof capture again.
Thank you.
And that concludes session. And so